Rice tables? Nah. I prefer ice tables.
Concentrations and reactions at equilibrium. Now, what are ice tables, you may ask? An ice table is basically a chart that we can use to simplify calculations in reversible equilibrium reactions, so we can find equilibrium concentrations of the reactants or products when using the opposite. So if we have an equilibrium concentration of the reactants, we can use that to find the equilibrium concentrations of the products and vice versa. Find the equilibrium concentrations of all species of 0.384 moles of CoCl2, which is phosgene, a type of poisonous gas, is allowed to come to equilibrium in a 5.8 liter container at 25 degrees Celsius, and after that they'll give us a equilibrium constant of 7.27 times 10 to the negative 40. And under that we see that they give us a balanced equation, with phosgene in its gaseous state on the products, an equilibrium sign, which means that the reaction can go forwards or backwards, and then carbon monoxide, CO, in its gaseous form, and then chlorine gas. Now if we take a closer look at the question, we can see that there are numbers to look for. We have 0.384 moles and then 5.8 liters. Since we only have moles and not moles per liter, we can use that and we can divide 0.384 by 5.8 to find our moles per liter for phosgene. So that's exactly what I do here. Step 1. Find the concentration in moles per liter. So we just talked about having the moles, and we talked about having the liters. So we can use 0.384 moles of phosgene, and divide that by 5.8 liters to get 0.066206, or 6.6 times 10 to the negative 2 moles per liter. Okay, so our next step is to create an ice table. Right now this may look really intimidating and confusing, but in the end you'll understand it, trust me. So let's begin with the first row, the initial row. This is where we put all of the concentrations before anything happens, which is basically before it starts coming to equilibrium. And so since we're only given the molar concentration of phosgene, that's the only number other than 0 that we can put in. So we're going to put it here under the first column in the initial row. And the other two, carbon monoxide and chlorine gas, we can put 0 in, since those concentrations initially are 0. We don't have anything in there. So on to the next row, the change. If you look at how many moles there are for each of the reactants and products, you can see that there is only 1 for each product and reactant. But also, we can see that because there's 1 mole of each product in the balanced equation, both of them will increase at the same amount when the system will reach equilibrium. So both of these will change by 1 mole. So 1 up here, which is 1 down here, 1 here, 1 here. And at the same time that the products are gaining 1 mole, the reactants are losing that mole. So down here, instead of putting plus x as like the products, we're going to put minus x down here. And so, on our equilibrium row, we're going to have 6.6 times 10 to the 2 minus x. And then we're just going to have x here, and also x here. Now, how to find x is in the next step. Now in step 3, by using algebra and our equilibrium constant expression, we can find the product's concentrations. So right now we can see that we have Kc equals Cl2 multiplied by Co over CoCl2. Now I rearranged that from the equilibrium numbers that we had in the last step. So now we have x multiplied by x over 6.6 times x to the negative 2 minus x. And so we can rearrange that equation a little bit, and we can sub in the number from the question in for the equilibrium constant. So our next step is looking just like this. X multiplied by x will give us x squared. Our equilibrium constant equals 7.27 times 10 to the negative 40. But you can see here we don't have that minus x like we had at the beginning. Now why is that? Essentially, if the Kc, which is the equilibrium constant, is anything smaller than 1 times 10 to the negative 4, there's really no point in using it, because it's going to be 0 anyway. It's going to be really, really close to 0 anyways. And so then we're going to have to use our algebra to find out how to get to x. And so what we do, we can multiply this side by 6.6 times 10 to the negative 2 to get rid of the divisor here. But since we multiply it on this side, we have to multiply it on this side as well. So what we're going to do is we're going to multiply 7.27 times 10 to the negative 40, which gives us x squared. And then to get rid of that x squared, we're going to take the square root of whatever 7.27 times 10 to the negative 40 multiplied by 6.6 times 10 to the negative 2 is. So this is going to be our equation to find x, the square root of the equilibrium constant multiplied by the equilibrium concentration of phosgene. And that will give us x equals 6.927 times 10 to the negative 21. 927 times 10 to the negative 21 moles have an impact. So as we can see in our last equation for the equilibrium expression, we have 1x here and 1x here, which is taking in place of Cl2 and Cl. And then we rearrange that equation so that we had a number here, Kc equals this number, and then we had x squared over 6.6 times 10 to the negative 2. So we can see here that x equals 6.927 times 10 to the negative 21. If we plug that into here, we should have the same answer, which is the equilibrium constant. So if we do our math here, this multiplied by this is that squared over 6.6 times 10 to the negative 2, or 0.066, and it gives us the same answer as the equilibrium constant, 7.27 times 10 to the negative 40. But that's also important because x equals CO and CL, which equals that same x, 6.927 times 10 to the negative 21. Phosgene equals 6.6 times 10 to the negative 2, which is how we found the molar concentration in the first question. And we can see here that 6.927 times 10 to the negative 21 moles is a lot less than 6.6 times 10 to the negative 2. Now, what does that mean for us? Well, it means that when the reaction reaches equilibrium, there will still be a lot of reactants left over in the system, since the equilibrium constant of 7.27 times 10 to the negative 40 is a super small number. So there's going to be a lot of reactants when the reaction reaches equilibrium. So this number right here means that the products won't have an effect on the normal equilibrium. That was my tutorial for ice tables. Thank you for watching, take care, and good luck with chemistry this year.